So in this part, we move to writing HDL to describe Rom. Technically, an FPGA does not have a dedicated ROM, so we're going to be writing code, and that code will be interpreted by Vivado either as a combinational circuit or as actually a lookup tables, and it will utilize its own lookup tables and combine a bunch of them to actually implement that. Because as you probably remember, ROM actually implements is a really large lookup table. So let's get started. So the way we're going to be doing it is in Vivado. I'm going to open up here. So I have a new file. So this file here. So this file in here, what it has really a couple of inputs. Because remember, a ROM, you can think about it as RAM, but you can't write into it. So just remove anything with the write, and you're going to end up with a ROM. So what I decided in here is that I decided to provide an address and just data, and the data is just an output. So there's no way for you to input data in here. So let's see, how can we write this particular code? Again, what we need to do first is actually to specify the memory, which is a 2D array. So I'm gonna specify that it will be 2 bits because my data is 2 bits in here, and I'm gonna specify that it will have basically 8 rows. Okay, that's how I'm gonna specify it, because the address in here is 3 bits, so I can get up to 8 rows, and the data here is 2 bits, so each word is 2 bits. Okay, so we're going to do this in here, and it's as simple as saying, okay, what you need to do is assign data equals ROM, because it is asynchronous, because as you could probably remember, a ROM does not need any clock here, so we don't even specify clock as an input. And that's pretty much it. So you specify memory, and then whatever you specify an address, it will actually just read out the output. And of course, data, each one of these bits can be implementing a specific combinational circuit or combinational function. Okay, so you might be wondering, like, okay, this is really simple. And if you probably go through the synthesis here or the schematics for the Rtl analysis, it will actually implement it as an Rtl ROM. But before I do this, I can't write to ROM, but I need to put some data into it. Why would I use it if I can't write anything into it? And as it turns out, Vivado and System Verilog allows us to do this. And it's a little bit strange because it borrows from the simulation. So we're going to be using the initial one because I'm going to only run it once. So I'm going to write into that memory, but I'm going to only run it initially when I first initialize it. And the way we're going to do it is initial. And as you probably remember, initial is very similar to always. It just runs once. And generally speaking, it's not synthesizable unless we're dealing with memory. So if you're dealing with memory, we're going to be using it. And what do? Well, we're going to use a system function here. And that system function tells me, let's read a memory. And that memory file, for example, is actually written in binary. You can do hex or binary. So let's start with binary. And I will just call it binary truth table. Okay, or let's just call it truth table for simplicity here, truth table. Okay, and I'm going to call it .mem, and you're going to see why in a minute. And it will be read from or written into the memory that I specified as ROM. And that's pretty much it. So again, this initial here, generally speaking, you shouldn't use it in your code. You only use it for simulation purposes, but if you're synthesizing and you're putting something on an FPGA, it's okay if you do it with memory. Actually, you can use this with any of the memory or any of the RAM that you have seen before. All of them, whether you're using BRAM or the other one, you can initialize your memory to certain values using this particular construct. All right, so now let's fill that truth table with something, okay, that file in here. So how do we get it? Well, we're going to go to resources and we're going to say add, and from add we're going to do create design sources in here, as you probably can see, and we're going to create that in here, and we're going to call create a file. All right, now that you can see it, we're going to do, instead of actually Verilog or Verilog header or system Verilog, what we're going to be doing is we're going to do memory file, and I believe we have decided to call it truth table. And you don't have to specify the .mem, but you're going to see that it will specify it by itself. We're going to see that it will call it .mem by itself. Okay, so let's do that. Okay, so we're going to click finish, and you can see that Vivado is actually running, and it will add something within the design resources. Now I do have something we call a memory file, and it's actually right there. So now all you have to do is just open it and put some data into it. And because it's binary, all you have to do is specify the binary per row. So let me just fill that for you. So I have filled this for you in here. You can see that I filled it with these particular patterns. And let me just put them on top of each other, the two files. you need to know the following. So this ROM in here is actually, each word has 2 bits. This is why I have 2 bits in each row, and I have 8 of these rows. This is why I have from 1 all the way to 8, and this is what I will be specifying it. So if you run the RTL analysis in here, okay, to see the schematic, so you can see that it actually implemented as an RTL ROM. It figured out that this is actually ROM. Okay, so now let's see if it's actually utilizing BRAM or lookup table. So I went to implementation and I clicked on run, and let's see what would happen. And as we expected, it did not use any of the BRAM. And if you think about it, it only used one lookup table, which makes sense because the address, which is what we specify as an input for the lookup table, is only 3 bits. And in the Arctic 7, we can have lookup tables up to 6 inputs. Okay, like each one of the logic cells can use its lookup tables as 2. Each one of them is 5 bits, or as 1, and its input is 6 bits. Well, I only have 3 bits, so I can just use 1 lookup tables, and I won't be utilizing fully. So 1 lookup table, that's exactly what we specified. So how can we actually force this to be in the BRAM? We're going to see this in a minute. But before we do, I want to make sure that this particular file in here, it's actually reading it in binary. You can do the same exact thing and move this and basically read it in hex. So if read mem h, you're going to be writing that particular file in here in hex. Instead of 1 0, for example, in here, that should be a 2, that should be then a 0, and so forth, and a 3, and you modify each one of these rows accordingly. This should be, I believe, a 1, and so forth, and you get the idea. So you can change all of them to hex and it will do the same exact thing. So now let's move to moving this into basically forcing it to use BRAM. Well, as the name implies, BRAM is just RAM, so it's not necessarily a ROM. So what we're going to be doing is we're going to hack our way through it. BRAM is synchronous. So what we're going to be doing is we will be utilizing that BRAM. We're just going to not utilize its input. We're just going to preload it with some sort of a data using this read mem. However, the ROM will be implemented as synchronous. So let me show you how we do this. Okay, so we're going to go to Synchronous Rom, okay, and we're going to do that. So in here, you're going to see that I have specified the inputs for the Synchronous Rom, and I called it Synchronous Rom, even though ROM usually does not take any input as a clock. It's just because I will be utilizing the BRAM to it, so I need to specify a clock. So now clock is an input. However, the rest of it is pretty much very, very similar. So let me just copy that code and specify it in here. Okay, I'm gonna copy that code in here, and of course now my logic, the way I specify the memory is the same, the way I load it initially is the same. However, now I have to use synchronous. This is here is asynchronous. So what you need to do is you need to use always FF at, for example, the positive edge of the clock. Okay, and of course now you're gonna have data, and it's non-blocking assignment rom.address. And that's pretty much it. This is how we force it to use BRAM. Now, technically, this should force it, but when I run it in Vivado, you're going to see that Vivado will actually figure out that it's too small to use a BRAM, and it's not going to waste a BRAM. So it will just implement it as a combinational logic or something like that. So what we're going to be doing is we will force it, and the way we're going to force it is by giving Vivado a synthesis attribute. So I'm going to give it a synthesis attribute, and that synthesis attribute usually lives between 2 stars. And what I will be doing is I'll tell it, hey, I need the ROM style to be blocked, basically use BRAM. That's what I'm forcing it to use BRAM this way. So if you run it that way, it will actually utilize the BRAM. So let's do that. And as we have expected, it actually utilized the BRAM as we wanted. No lookup tables, no flip-flops. And again, I called this file Synchronous Rom, which is different. ROM usually it implements combinational circuits. There's no clock, and the reason why it's synchronous this time is just because I am utilizing the BRAM. So it's as if you can think about it, I'm wrapping the BRAM with some sort of a just read functionality and no write functionality. There's no way for me to write into this RAM. I'm just basically initially loading it with something, and this particular synthesis attribute that I instructed Vivado to use BRAM for it.